In today's economy, cash flow is tight, and families are held captive to high interest rate credit card debt. Churchill Mortgage can restructure your current mortgage and significantly reduce these problems. Get a free analysis and learn how to eliminate credit card interest rates, lower bills, and start taking control of your budget. Get started at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLSconsumeraccess.org. Equal housing lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
The holidays start here at Baker's with a variety of options to celebrate traditions old and new. Whether you're making a traditional roasted turkey or spicy turkey tacos, your go-to shrimp cocktail, or your first Cajun risotto, Baker's has all the freshest ingredients to embrace your traditions. Baker's, fresh for everyone.
Choose from a great selection of digital coupons and use them up to 5 times in one transaction. Check our app for details. Baker's, fresh for everyone.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on Space Nuts. It's all about astronomy, space science, and all sorts of stuff. We've got a lot of stuff to talk about today because it's episode 280. And because of that, we're going to dedicate it entirely to audience questions. So thank you for sending them in. We do love to hear from you. And we've got questions from all over the world today, which is fantastic. It's lovely to have a global audience. I am your host, Andrew Dunkley, and joining me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
How are you doing, Andrew?
I'm doing as well as I can.
Very good. I'm sorry, I'm slightly distracted because I've just realised that this is coming to you not via the normal microphone, and I don't know why, because the normal microphone is plugged. The normal microphone's plugged in. Never mind, it's all right. Onwards and upwards. You can obviously hear me.
Yes, I can. We'll just use some of that magic stuff to
tweak it later,
fix it up.
But it means I can take these out. Take the head.
Oh, okay.
Because it's coming through the loudspeaker.
There you are. All right. Now, we've got questions today. We're going to sort of mix up the audio and the text questions. So John wants to talk about gravitational waves. Brett wants to talk about that mystery signal we've mentioned before. The James Webb Telescope's on the agenda. Space junk. Origin of universes is an interesting question. We'll also be looking at gravitons and dark energy. But before we do all that, I thought you'd like to hear this one, Fred. It's just an email. It's not a question. It comes from Michael. Hello, Professor Fred. While listening to the most recent episode, I heard you mention that you had, earlier in your career, done work on the orbit of the Psyche asteroid. My daughter works for JPL as a systems engineer and is currently assigned to NASA's Project Psyche. She's in good company then. Best regards, Michael. Isn't that lovely?
It's lovely. I think it actually means I'm in good company, not she's in.
Oh, well, that may well be the case, yes.
Yeah.
I actually saw something the other day about the asteroid Psyche, and they said it has enough gold in it to make every person on Earth a billionaire. But if that were to happen, then it wouldn't be, the price of gold would plummet, I imagine.
It would, yeah. Yes, it's probably a metal asteroid, or mostly metal, highly metallic, if not purely metallic.
Indeed it is. A couple of other things.
When I was studying it, all it was a dot moving in the sky. Nobody knew what it was.
It's a bigger dot now. The other couple of things we needed to talk about, we got an audio, not question, but observation from Peter on the Gold Coast the other day, because he noticed, and a few other people have noticed over many episodes, that you do cough occasionally. And he thought maybe you should change your milk and try A2.
So I did.
And?
Yeah, Peter, I've done what you advised, and we'll see what happens. I haven't coughed.
Yeah. No, we'll wait and see. And Peter Verweyen, another Peter, is someone you want to shout out to.
Yeah, hello, Peter. One of our regular listeners and maybe even a watcher as well, a former colleague of mine at Siding Spring Observatory, now doing his PhD on MOND, the Modified Newtonian Dynamics theory, which is an alternative to the idea of dark matter. And we follow Peter's research with interest because you never know. One day, the Mon theory might turn out to be right. But Peter was very generous in his congratulations on our success at reaching 1 million downloads a year. So thank you, Peter. And I'll get around to answering your email when I can.
Wonderful. All right. Without further ado, let's go to our first question. This comes from John in the UK.
Hi guys, it's John here from Burnley, northwest of England. I've been listening for a while now. I think your podcasts are fantastic. Keep up the good work. My question is regarding the gravitational waves that you spoke about last week and the LIGO experiment. How do you tell where they come from? In which direction do they appear to be coming from? And do they come through the Earth as well? Obviously, normal telescopes, you can't see through the Earth. So is that something that can happen? And obviously, how far away are they and how do you detect that? Thank you, guys.
Yeah, thanks, John. Lovely accent, by the way. It's really good.
Hey, by gum, I can do that better than you can. Hi.
Yeah, I'm sure you can.
And I should say that Burnley, actually it was always Burnley when among my family, is just the other side of Pendle Hill in Lancashire from the Watson family seat, which is Clitheroe. It's where a lot of my ancestors came from. Clitheroe is just over the hill from Burnley. So very close to my heart. John, thank you for your question. Well, what was the question again? No, it's all right.
So, well, where do they come from? How do we know where they come from? What direction?
My mind's just on those lovely parts of East Lancashire. Okay, it's a really great question, which we've touched on before, but not really analysed in detail. And it's all about having multiple detectors. So the original LIGO has, which is the Laser Interferometer Gravitational Wave Detector, is actually two of these instruments. Remember, they're 4 kilometre long tubes, two pairs of them placed at right angles to each other with laser beams bouncing up and down them. There's a picture of one of them in this book that you've heard of before, Andrew, Starts with a Space Walk. I can never remember the damn title of this book.
You're going well, Fred.
Because I do talk about gravitational wave detectors, and I actually sketched one in a cartoon. But there are two of them, the LIGO detectors, and they're at opposite corners of the United States, so they're separated by 3,000 kilometres. And that is partly to eliminate any kind of terrestrial disturbances like earthquakes or trains going past, because remember, these things are highly sensitive to vibrations. That's what they're detecting. They're actually detecting vibrations in space. So they need to eliminate other things. So having two does that. But also having two gives you an idea, at least, of what direction the gravitational waves are coming from, because we know they travel at the speed of light. And so one of these detectors picks up the gravitational wave, usually picks up the gravitational wave before the other, and measuring the length of time, the time delay between them, gives you at least a first estimate of the kind of direction in as far as whether it's a northern or southern hemisphere, for example. Yeah. But then you add to that Virgo, which is the Italian gravitational wave detector in Italy, and that gives you another point to let you triangulate where these things are from. There's a new one coming online. I don't think it's operational yet, Kagra in Japan. And as you build up more of these detectors, you're able to triangulate and get a better estimate of where they actually come from.
Interesting.
Sorry, go on.
I was just going to say, it's also interesting that they seem to be putting these things in high earthquake zones.
Well, yeah, that's right. Just to make it hard for themselves.
Yeah,
indeed. So, but the other thing is that having multiple detectors, so every gravitational wave signal has a really characteristic fingerprint, if I can put it that way. It's the combination of the way the frequency changes, the frequency of the vibration in the wave, and how its amplitude changes, the amount of the vibration, and the sort of timescale over which all that happens. That's the signature that you're going to get identically in each of those detectors. That's how you know that it's a real phenomenon, and it's by, what you can do then is slide them all together in software, and that gives you a really good estimate of where they've come from, and that you're looking at a real signal rather than an earthquake. So it's also that characteristic shape that gives you the details that we're hearing about gravitational waves. The identity of the source of the gravitational waves, usually colliding black holes or neutron stars, and the distance as well, which comes from essentially the strength of the signal, but also some of the aspects of the wave itself. So all that is teased out of this fleeting vibration that comes from space, just something that wobbles the mirrors of the detector slightly, and then allows you to deduce all this incredible information from it. So
now, he also asked if a gravitational wave goes through Earth, or does it bounce off when it hits us?
No, straight through. It's
straight through.
It's space itself that's vibrating. Of course, the Earth sits in space. So
okay. All right. Well, that prompts a question. We got two questions from Brett in Pennsylvania, and one of them was gravitational wave related. He wanted to know what would happen if you were very close to the source of a gravitational wave. So if you were nearby when two neutron stars collided or something, what would happen to you then?
It would be, the amplitude of the waves would be very high then. And so you would, it could well be that you're spaghettified in the same way as you are with a black hole if the amplitude is enough. It's quite right that the intensity of the waves falls away. It's an inverse square. Actually, that might not be true. It's not. I don't think it is an inverse square law. I need to check that again. But it falls off very rapidly with distance from the source of the waves.
So don't get too close.
Don't get too close. That's right.
Yeah, I actually did write about that in my sci-fi book, The Turanian Enigma. But in my book, the spaceship was hurled along by the wave, and
it surfed it, surfed the wave.
Yeah,
lovely,
surfed the wave, yeah. But not very elegantly, I might add. All right, so we've covered John with his question about gravitational waves, and I sort of dovetailed into Brett from Pennsylvania. And thanks for your question, John. So let's move on to Brett's other question. He said, "Hi, friends. I recently read about an object ASCAP J1736008.2-321635. Damn it, that's my email password. Anyway, that object is near the centre of our galaxy, and that produces odd, unpredictable radio signals. Seems nobody knows for sure what is creating them. My question is for both of you, what do you think the signal is, and what would you like it to turn out to be? Thanks, guys, for everything you teach. Love the show." Thanks, Brett. And I would like it to be talkback radio. And I think it's talkback radio because we could learn a lot from talkback radio. It would all be garbage, but it could give us an insight into what's going on in other parts of the galaxy. To be honest, I've got no idea what to consider. I would suspect it's some kind of natural phenomenon that we are yet to identify, but I think Fred's better positioned to answer that one.
Well, yes, that's right. It is an unidentified celestial, or an unidentified type of celestial object. Let's get it right. So a report quite recently, which made the headlines throughout the world, that I'm reading here from the University of Sydney's press release, because the astronomers who worked on this, and it was using ASCAP, the Australian Square Kilometre Array Pathfinder, that giant array of dishes in the Murchison region of Western Australia, which is a pathfinder for the Square Kilometre Array. And so what is fascinating about this is that astronomers at the moment really don't know what's causing it, and wonder if what we're seeing is the effect or evidence of a completely new type of celestial object. Can I quote from one of the authors of the paper, a PhD student?
Sure.
Ziteng Wang, I think is his name, is the lead author of the study and a PhD student in the School of Physics at the University of Sydney, where, by the way, I've got an honorary position, which is delightful. And what he says is the strangest property of this new signal is that it has a very high polarization. Now, many of us are familiar with light being polarized because we wear polarizing sunglasses, but radio waves can be polarized as well. This means its light oscillates in only one direction, but that direction rotates with time. What he goes on to say is the brightness of the object also varies dramatically by a factor of 100. And the signal switches on and off apparently at random. We've never seen anything like it. And that's it.
Wow. What would you like it to be, Fred?
Yeah, that's a really good question. What I'd like is for this to be something that sheds light on one of the other big mysteries, like dark matter. I think it's too much to hope that it's and it's got the wrong characteristics for it to be evidence of interstellar intelligence. I think it might, though.
In which case, my talkback radio theory still holds up.
Yeah, that's right. I'm not really going there, I don't think. I mean, I think we pride ourselves, Andrew, on having a very high quality of talkback on Space Nuts.
One would hope so.
Yeah, we hope so. So, yeah, it would be great if it was something that, as often happens, and this has happened with the fast radio bursts, that it's a mystery as to what causes them. We think we've got some idea of what it is now, flares on magnetars, but the observations of those fast radio bursts actually opened up some new research in the density of material in intergalactic space, a fantastic thing. So maybe this object, whose name I'm not going to recite again because it's your phone number, that object might also give us some new insights. It is coming from the center of our galaxy, so that's an interesting place, which still has a lot to tell us. It's actually an area of the sky that I studied back in the 1970s, looking at bog standard variable stars rather than weird exotic objects that emit polarized radio radiation.
So the bottom line is, Brett, don't know.
Watch this space, I think.
Yeah. DUNNO, by the way. That's how you spell dunno. But thanks for your question. A very quick one to finish off this segment from Walter. Hello, Andrew and Fred. I'm in Springfield, Vermont. Do you know how long after launch the Webb telescope will unfurl, the James Webb Telescope, which I believe the launch has been put back to the end of next year now? Does it do so before it reaches its parking spot or only after? Love you, Walter. Oh, love you too, Walter. Thank you. Do you know the answer to that one, Fred?
Yes. There's a really good site that's the webbtelescope.org website, and it's got mission and launch quick facts on it, and that's got all this information. It still says launch scheduled for December 2021 there, though.
Oh, okay. I'm pretty sure I heard in the news that it had been pushed back.
I'll be sorry to hear that if it has, but
now I need to double check.
Yeah. But the answer is it takes about a month. One of the questions in this is how long does it take for Webb to reach its orbit? Webb is designed to travel for about a month to reach its orbit at the second Sun-Earth Lagrange point, L2, 1.5 million kilometres from Earth. There you go, 940,000 miles.
Yes, I see a headline here. James Webb Telescope launch delayed again to maybe December 22 rather than the year 2022.
Okay, because it was yeah, there you go. It was December 18th. That was the...
Okay, so it's only a few days, not a year.
Yeah, that sounds more...
When I saw 22, I assumed it was the year 2022. Ah, dear. See, it pays to be a really good journalist in my job.
Well, at least you check your facts. It's just you do it after the event.
Yeah, I did it after I said it. Anyway, please accept my correction.
I recommend that website, Mission and Launch Quick Facts.
All right, very good. There you go, Walter. Thank you. And you are listening to Space Nuts. I'm Andrew Dunkley, and he's Professor Fred Watson.
In today's economy, cash flow is tight, and families are held captive to high interest rate credit card debt. Churchill Mortgage can restructure your current mortgage and significantly reduce these problems. Get a free analysis and learn how to eliminate credit card interest rates, lower bills, and start taking control of your budget. Get started at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591, NMLSconsumeraccess.org, Equal Housing Lender, 1749 Mallory Lane, Suite 100, Brentwood, Tennessee, 37027.
Roger, you're loud and clear here also.
Space Nuts.
And thanks for joining us. If you'd like to become a patron, don't forget you can do that just by visiting our website, spacenutspodcast.com or spacenuts.io, and click on the supporter tab. As a patron, you'll be putting a few dollars in our bucket every month to keep us up and running, which we certainly appreciate. And don't forget the 30-day trial on Patreon and Supercast. You can test it, see if you like it. If you do, that's great. If you don't, you can dip out. That's fine as well. But you can find out all about it on our website. There are other ways of supporting us as well. You can send us love letters like Walter did, or you can make a one-off donation through whatever channel you choose. It'll all be there on our website, spacenutspodcast.com or spacenuts.io if you'd like to become a patron. We appreciate it, but it is not mandatory, as we continually say. Now, Fred, let's go to our next question. I think this one comes from Sean in the United States.
Hi, Andrew and Professor Watson. This is Sean from Charleston, South Carolina, U.S. again, talking about space junk. The Russians just launched a killer missile to take out a target satellite in fairly low Earth orbit and created a boatload of space junk. The Chinese also launched a missile a few years back and took out an old weather satellite, adding more junk. So between all the junk that these two countries have, how do we stop them from doing it? I don't know. The UN, people have to get together because they're ruining the Earth's population in space, which isn't theirs. So that's my question. It's kind of technical, political too, I guess. But thanks a lot. I love your show. I listen to it all the time. You guys are great. Thanks.
Thank you, Sean. Lovely to hear from you. You raise a very complex issue because there's no simple answer to it. And it seems, particularly with the recent Russian missile tests, that two different organizations in Russia weren't talking to each other, the space agency and the military. And there were two Russian cosmonauts on the ISS, which was obviously perceived to be under threat as a consequence of the space junk that was created by that anti-satellite missile firing. And it's not just China and Russia. I mean, just about every country that's put something into space is responsible for a lot of the junk that's out there. So it's a wider problem than that. But I see where you're coming from in terms of missile tests creating massive amounts of debris in a very, very short period of time. And yeah, how do we stop it? Negotiation, I suppose. Fred, what do you think?
Well, first of all, it's not just the Chinese and the Russians who've done that. The Indians did, and so did the Americans. So, as you said, everybody's kind of responsible. But it does actually contravene the principles of the International Space Treaty of 1967, which says that you shouldn't do things in space that are detrimental to others. And of course, by creating space junk, you're doing that. You're putting a huge risk up there for not just human occupied spacecraft, but robotic ones as well. However, so in fact, tomorrow, Andrew, I'm leading a discussion about satellite constellations in the government department I work in as an information thing. And as part of that, I've been talking with a very eminent space lawyer here in Australia, Cassandra Steer of the Australian National University. And her take on this is that the signs are promising for some sort of UN mandated treaty that will stop this happening, because everybody realizes it's dumb and that the risks are great. And Cassandra's got her ear much closer to the ground on issues of space law than I have, and it was quite encouraging to see her comments about that. So yeah, exactly as Sean said, it's a difficult problem. Ultimately, of course, you've got Kessler syndrome hanging over us, with the possibility that you might make space completely unusable by this cascade of collisions. And so the hope is that perhaps before too long, maybe you and I, Andrew, will be talking about some new international agreement, which comes from the UN body, the UNOOSA, the UN Office for Outer Space Affairs. It will be great to be able to report on that. So fingers crossed, the signs seem to be good.
Yeah, I suppose the other question is, you mentioned that it is actually contravenes the current treaty. What's the penalty? I mean, obviously, there's nothing much you can do. It's a gentleman's agreement.
Well, yes, that's right. In many ways, in fact, Cassandra, she actually recorded a segment for us for this discussion because she couldn't make it. But she did talk about the treaty in detail, and it is that sort of agreement, but it underpins a lot of more detailed space law. And so I guess what you've got to do is build up the details that are based on the treaty, the detailed legislation, and make it international. That, I think, is the trick. So, yeah, but really interesting question, something very interesting. But I think things move very slowly in this particular area of legislation. So it might be 5 years or so before we see anything.
Yes, and you're talking about organisations within governments that don't always see eye to eye, and you risk diplomatic issues if you point the finger. I mean, the United States was pretty heavy in its criticism of Russia over this latest test, but as you said, they've done it before as well. I don't know. I don't know what the solution is. Hopefully, yes, a new agreement and a new approach to it will rekindle the attitude to be in a more positive and cooperative direction.
Yeah, it's what you said at the beginning, Andrew. It's negotiation. That's what we need.
Yeah. I truly believe everything can be negotiated. It's just sometimes we're very quick to do something before the negotiation process, and that's where things come unstuck, I suppose. Okay, Sean, thank you. Good to hear from you. And now we've got a text question from William. What I know about our universe is that stars come out at night, just like my teeth. My question is it possible that our universe originated from a black hole and that other universes were created in the same way? Since we've not discovered other life in this universe so far, once life ends here, our universe will be dead. So sad. Yes, I agree with that, William. Interesting observation. Well, hopefully we will find life beyond Earth, whether it's intelligent life or not. That's a giant question mark. But what about the idea of the universe being created out of a black hole and other universes thereby?
Yeah, so that's one of the dominant theories about multiverses, multiple universes. And I think it originates with Roger Penrose, the well-known mathematician, in fact, Nobel Prize-winning mathematician. Interestingly, tonight I'll only be emceeing it, but we have something here in Australia called the Allison Levick Lecture, which has been held by the what used to be the Anglo-Australian Observatory every year since 2021. It's a public lecture given by a speaker of some eminence, and this evening's lecture will be given by Professor Catherine Haymans, who's the Astronomer Royal for Scotland. Now, her specialty is exactly this, and her talk tonight is entitled Mysteries of the Multiverse. Now, by the time this podcast goes to air, that will be in the past. However, it is possible for people to download it and have a listen because we're going to record it. And if you look for Allison Levick Lecture, it's ALLISON LEVICK Lecture. I'm sure you'll find it. It will be on the Macquarie University website. So have a look for that. And the reason why I'm being cagey is that I'm hoping to learn a lot more about current thinking on the multiverse than I've read already. So it'd be good to hear, Catherine.
Yeah, I suppose this is the way my brain works. We've learned that there are multiple planets in our solar system. We've learned that there are multiple solar systems in other parts of the galaxy. We now think we've discovered other planets in other galaxies. It stands to reason that with multiple planets, multiple solar systems, multiple galaxies, multiple universes.
Yeah, maybe. The trouble is there's a definition problem there because a universe means everything we can ever observe or understand. And so the idea of multiple universes is a bit contradictory, but it's one that certainly, is envisaged. And I guess the normal way that people think of multiple universes is by invoking additional dimensions. So you've got, some higher dimensional space in which these universes sit. That's the sort of thing I'm hoping we might hear from Catherine tonight. We'll see.
Okay, so if you'd like to catch up with that lecture, you could probably download it now through the Macquarie University website. The Allison Levick Lecture is what you'd be looking for. This is Space Nuts. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
All right, Fred, because it's episode 280, we're committing it all to two questions. And our next question comes from another part of the world you're very familiar with. This is Barry from Fife.
Hi, Andrew. Hi, Fred. This is Barry with another question from the East Nuke of Fife in Scotland. Fred, a couple of times recently I've heard you mention the possibility that a hypothetical graviton particle might be responsible for gravity. And I can't get my head around this. I don't see how that fits in with Einstein's theory and the description of gravity as a distortion of space-time. I actually looked up a couple of articles online, and when they started taking me deep into quantum theory and string theory, I just had to give up. And I was wondering if there's any way you could possibly give us an idiot's guide to how this graviton might actually work. Thanks a lot. Bye.
He opened the door on that one. Fred is just the person to give you an idiot's guide to to gravitons. To be honest, though, gravitons really put a lot of pressure on Fred, so it really weighs him down. Can I do any more really lame dad jokes, or is that enough?
I'm sure you can do better than that, Andrew.
No, I can't. No, I can't. Dear, oh dear. It's a good question, though.
It's a great question. It's always good to hear from the East Nuke of Fife as well, which is very, very close to my heart, as you know. Not just because one of my daughters lives not very far from there in Dunfermline. I spent a lot of my life in St Andrews. It is hard to get your head around this. And the perhaps the way to think of it is to go back to the idea that we know that fundamental particles can be both, or are both, waves and particles. They've got this dual characteristic, which is why light, for example, exhibits characteristics that tell you it's a wave, but also others that tell you it's a particle. Not only that, it tells you it's a particle that can be in two places at the same time. So it's really that dichotomy is present throughout the whole of fundamental physics. Now, the force particles, like the photon, the gluon, which carries the strong nuclear force, the Z and W bosons, which carry the weak nuclear force, they are particles that their sort of perception on a macroscopic level, in other words, the way we see things on the big scale, leads us to see them as a force. And that's how Newton perceived gravity. It was Einstein who said, actually, it's not a force, it's a distortion of space. But when you think about it, the force analogy works incredibly well. It works so well that we don't really need to use relativity until you start dealing with extreme gravitation and velocities. You've still got this dichotomy because we know that these forces are carried by fundamental particles, but we perceive them as forces. And in many ways, the graviton is a little bit like another of these force fields, or force field particles, which is the Higgs boson, because the Higgs boson is that particle that gives other particles the property of mass. But it was first recognized by the idea that there was something called the Higgs field. This is what Peter Higgs deduced back in the 1960s, that there's this field that permeates space that gives particles the property of mass. And wherever you've got a field, you've got to have particles to carry it on the subatomic level. And the same is true with gravitation. Gravitation is a field, even though we recognize it as a distortion of space and time, by the way. But being a field, it needs to be carried by a particle. The graviton is the hypothetical particle that will do that, but it has not yet been discovered. None of the experiments that have been done with particle accelerators have yet seen anything that could be the graviton. And in fact, the properties of a graviton, and I suspect this is what Barry ran into when he started digging deep into this, because it's highly quantum mechanical. But the properties of a graviton are actually, they're well understood. Let me just refer, if I may, there's a very good entry on this on Wikipedia, but it is highly technical because of quantum mechanics. But the last sentence of the introduction says, this result suggests that if a massless spin 2 particle is discovered, it must be the graviton. So its properties are well understood, but we haven't found it yet. It's one of the curiosities of particle physics research. I don't know whether that helps Barry with the dichotomy. Maybe the way to think of it is that, at some really fundamental level, there are these particles, but we see them as something else. We see them as either a force or a distortion of space-time, which is Einstein's relativity theory.
Yeah. Well, we know there are photons.
Yeah, exactly.
And I'm guessing that we are assuming dark matter is some sort of particle as well, or created by or carried by some sort of particle. It looks like particle physics is going to probably be the answer to a lot of these mysteries. It's just we're really only in the early stages of really delving into this stuff.
Yeah, that's right. We've only been doing it for 100 years.
Yeah, it's not long.
And it's hard. It is really hard to understand what's going on with all these things.
Well, it's certainly it's a needle in a haystack, but the haystack's as big as the universe,
and the needle's as small as a photon.
Yeah, exactly right. Barry, lovely to hear from you. Love the accent. I know. You're going to say you don't have an accent. I have an accent. I've used that joke before. But yeah, lovely to hear from you. Now let us move on. By the way, if you are into social media, don't forget to join our Facebook page. Just do a search for Space Nuts Podcast on Facebook, and you'll find our Facebook page, our official Facebook page, and we've got a lot of followers there. But we have a listener-generated Facebook page as well called the Space Nuts Podcast Group, so you can join that one as well. There's around 2,200 people who are following that page, and it's where you can get together and talk to each other as Space Nuts listeners. And it's very, very active. So please do so. And I'm pleased to announce that we now have an Instagram page, an official Instagram page. So if you have Instagram, which is basically just another version of Facebook on a different platform. Spacenuts.io is the name of our Instagram page. So if you'd like to join in with that, we'll be putting a lot of material on Instagram as well. So took us a while, and thanks to Marie Claire in the United States, whether she's in New York or Miami at the moment, I'm not sure, was her idea that we should move onto that platform, and we did it. So spacenuts.io if you want to join us on Instagram. We have one more question left, Fred, and this one comes from Michael Blanchett. No relation to Kate, I suspect. I just listened to episode 120. He's a little bit behind. And you guys stated that if you had two steel plates in a vacuum of space would push the plates together. So if we also know that for every action there is an equal and opposite reaction, would it be safe to say it's dark matter, dark energy? Because it would be pushing empty space out as well, if that makes sense. Also, your podcast is fantastically awesome. I don't think we've been called fantastically awesome before. We've been called a few other things that we can't repeat on air. But, yeah, that's great. Oh, yeah, that's a big question, though.
It is. And, the bottom line is that the effects of this force are well understood, and even when you take them into account, you've still got the problem of dark energy. It's not understood at the quantum level. It's a fairly familiar saying. I haven't checked this recently, but if you think of dark energy as a quantum physics process and make a few assumptions, you get an answer that says that dark energy is 10 to the power 120 times more than what we actually physically observe. So the physics, are not well understood of dark energy. The physics of the Casimir effect are, however, this is what I think we were talking about in episode 120, named after a Dutch physicist, Hendrik Casimir, who actually made a prediction that this should happen back in 1948. And it was, in fact, almost 50 years later, 1997, that it was quantitatively measured. The force was measured in a laboratory, got some very close to what Casimir's prediction was in the early days. So it's all about quantum physics, because it's the vacuum fluctuations in space that push together these plates. So I'm not even sure whether there would be a reaction, because the moving of the plates, I think, is a reaction to the vacuum fluctuations themselves. Or the force on the plates is the response to the vacuum fluctuations. So I think dark matter theorists have come to the conclusion that it doesn't work.
Could be the dark side of the force.
That could be it. The force is always with you as well if you're in a vacuum.
They weren't far off, I know it's science fiction, but sometimes they glance the nail.
They do. Oh, what a lovely way of putting it, Andrew. Glance the nail. I like that very much.
Glance the
nail.
Have
to use that in something.
Yeah.
Have you used it in one of your books? No.
No, I haven't used. So I'll give that one to you.
Thank you. For
a small fee. No, not a problem at all.
Okay.
Did we finish that question?
I'm afraid so. The people who are working on dark energy theory are extremely competent physicists, and they really understand well how these microscopic phenomena, if I can put it that way, like the Casimir effect, work. So I suspect, that sort of raises perhaps a bigger question. When we do work out what dark energy is about and what's going on, will it be a completely new discovery and totally new insight, or the realization that, yes, we've been missing something? Two slightly different things there. My guess is it will be something completely new, because so many turns have been upturned with a glancing blow at the nail. Can I mix metaphors? No, it doesn't work. Yeah. But, you know, there are very few stones that are left unturned in the world of this kind of physics, if I can put it that way.
Yeah. So it's got to be, well, theoretically, it's got to be something completely different and new and unknown to us at this point.
Exactly.
All right. We wait with interest. Hopefully we won't be a lot older by the time we figure it out. But
that's right.
Time will tell. Thank you, Michael. Lovely to hear from you. Lovely to hear from everybody. Thanks for your questions. It's always great fun. And if you do have questions for us, don't forget you can visit our website and you can click on the AMA tab where you can type your question like old people do, or you can send us a voice question with the recording device built into the AMA tab, or you can, on the right-hand side of our page, you can click on the link there, send us your voice message, it says. So it's as simple as that. And we do love to hear from you. Don't forget to tell us who you are and where you're from so that we can share that with the world and they can rob your house. Or not. No. All right. Thank you very much again. And thank you, Fred, as always. That brings us to the end of another program, episode 280. Can you believe it?
I know. And listen, Andrew, no cough.
Yeah.
Peter.
No cough. A1 suggestion.
Yes, that's right. And I'll see you next week, I hope.
I hope so too. Look forward to it. Thank you, Fred.
See you later.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and Hugh back in the studio, who's got himself a new habit. He's into chewing gum, which means that his voice is completely distorted every time I try and ring him up. You know, it's been around for thousands of years, Hugh. It's not new. Anyway, thank you for your company. Look forward to catching up with you on the very next episode. See you soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.